Alright, we're looking at the Unit 4 review. First problem says, an object is accelerating at 5 meters per second squared to the right. Calculate the net force acting on the object. So we can use the formula force equals mass times acceleration. The mass of the object is 3 kilograms, while the acceleration rate is 5 meters per second squared. When you multiply those together, you get 15 newtons. Number 2. It says calculate the acceleration of an object at the right. We're given two forces moving in opposite directions, and we're given the mass. When we subtract the two forces, we get 18 newtons. Then we can apply this to the force formula. In order to solve for acceleration, though, we're going to have to rewrite it as acceleration equals force divided by mass. Our force, we know, is 18, while our mass was 3.5. So when we do the math there, you end up with negative 5.1 for your acceleration. And that makes sense because it's moving towards the left, the negative direction, on a number line. Number 3. This one's a little more challenging. We have a scenario where you have a hot air balloon that is pulling up on a box that weighs has a mass of 2 kilograms, but it's still descending. So the entire thing is falling at 2.8 meters per second squared. So if you'll remember, we're trying to find the net force of the entire scenario there. We can take the 12 kilograms and multiply it times the acceleration rate of the balloon with the box. Keep in mind that if we're trying to find the tension of this, we're going to first have to identify all the forces acting on this. So our free body diagram is drawn here. You have the force of tension and the force of gravity. So now, in order to find the force of tension, like they're asking us to do, what we have to do is we have to take the total net force that we found just a minute ago here. We're going to have to subtract that from gravity. There's several ways you could do that. First, you have to find gravity. So I'm going to go ahead and write this out the way it is. Remember, net force is going to be your total for your tension plus your gravity. I'm going to go ahead and do algebra to get the tensional forces by themselves. So the total force minus gravity is going to give us our force of tension. But in the end, all we're really doing is we're taking the force of gravity and subtracting it from what we got earlier, the net force. That should give you 86.4 newtons. Notice the acceleration rate of this is in a negative direction. Number 4. This scenario, we have an elevator. The lady on the elevator is descending. She has a mass of 50 kilograms and she's descending at 8 meters per second squared. So I'll go ahead and draw my force diagram here. Notice we have force of gravity and we have a force normal this time because she's standing on a platform there. The net force is equal to mass times acceleration, so we're going to find the whole force first by multiplying 50 times 8. That gives us 400 newtons. Then we're going to look at the net force of all the forces that are involved. We have your force normal plus the force of gravity. This time we're going to get force normal by itself by subtracting gravity from both sides. So when I begin plugging my numbers in, again, basically it's like we did last time. We're subtracting the gravitational force from the total force to get the force normal. So 50 times 10, 50 is your kilograms, 10 would be 9.8 meters per second squared, rounded. And that, whenever we subtract 400 from 500, you end up with 100 newtons. And it's positive because we're looking at the normal force. That's what we're trying to solve for. And normal force is pulling up. You'll notice the 500 there is the force of gravity pulling down, so it should be negative. Number 5. Got a dog named Bim. He's trying to pull a box that has a mass of 5.2 kilograms. He's applying 22 newtons of force. So drawing our force diagram, free body diagram here, we have the force normal, your force of gravity, your applied force, and your frictional forces. They're asking us to find the force of kinetic friction and the force of static friction. These are the formulas that we can use. It's just the force normal times the components of static and kinetic, and they give those to you. So the force of kinetic is going to be 0.2 times 5.2 times 10. Again, we multiply the mass times the rate of acceleration for gravity to give us our force normal. The reason that works is because the force of gravity is opposite normal here in this drawing. So we're going to do the same setup for each one of these, just plugging in the different components, one for static and one for kinetic. Remember, static friction is going to be the friction that stands still, while kinetic friction is the friction that occurs during movement. The next question it asks is, if the object started at rest, does it start to slide? And the answer to that question is, yes, indeed it does. And how can we prove that? Well, if we look, the dog is applying 22 newtons of force, and the static friction, in other words, the friction of sitting still, is 18.2. So since 22 is greater than 18.2, yes, he should be able to break that. The next question asks, if the object is already moving, they want us to calculate the acceleration. So we're going to use, again, mass times acceleration. You'll notice that this time we've got our applied force minus the force of kinetic friction, which is going to give us 11.6. We know that our mass is 5.2. And we're multiplying that times acceleration, which is what we're really trying to find. So we're going to rewrite this formula so that we can solve for acceleration. So 11.6 divided by 5.2 gives us 2.23 meters per second squared. Number 6 is really just a matter of recognizing what's going on with Newton's third law. The force of gravity pulling down on BIM is the opposite of BIM pulling up on the Earth. The force of tension pulling on the mass is really the opposite of the mass pulling on the rope. The normal force of the floor on BIM's feet is the opposite of BIM pushing on the floor, and the force of friction on the floor on a block is the opposite of the block's friction on the floor. So those are all, according to Newton's third law, equal and opposite reactions. Number 7 is asking, why does normal force acting on an object not work as the Newton's law action-reaction pair for gravity? And the reason behind that is normal force is a contact type force. Remember, it has to be perpendicular to the surface, while gravity is a force from a distance. They have to be the same kind in order to be a normal action-reaction pair. All right, on the back, number 8. Again, this is a straightforward one using the force of mass times acceleration. These are our quantities that are given, 30,000 kilograms and 8.8 meters per second squared for your acceleration. When you multiply those together, you get 264,000 newtons. For number 9, this time it asks you how much force is needed to accelerate a 0.4 kilogram ball from rest to 30 meters per second in 0.2 seconds. In this one, we can use the force formula, but we aren't given acceleration this time. We have to find that first. So they do give us our final velocity, initial velocity, and time. So that means we can use our acceleration formula. Plug in our numbers there, which gives us 150 meters per second squared. Then you can simply multiply the mass times the acceleration to find the amount of force that's necessary. That comes out at 60 newtons. Number 10. This one kind of throws people because whenever they ask the question, they're not paying attention to which direction these people are coming from. So if you'll notice, we have the 250 force north, 250 newtons moving towards the south. It says the football player pushes south with a force of 250 when he's tackled by 3 other players. If he's hit from the east by a player from 120 with 120 newtons, that means he's moving towards the west. He's hit from the north by 2 players with a force of 150 newtons and 130 newtons. So what we can do first is add all of those forces that are going in the same direction together. So that's 130 plus 150 plus 250, which should give us 530. The other force is 120 newtons towards the west. So we can't add that one directly to it. Instead, we need to plug that into, put those forces together there so that we can solve for the hypotenuse, which is going to give us 543 newtons. That's going to be the resultant for those forces. Notice it's moving in a southwest direction there. So the answer is 543 newtons southwest. That's the total net forces of the entire situation there. Okay, this next one is dealing with tug of war. It says 2 groups of students pull in opposite directions in a game of tug of war. If Team A pulls north with a force of 480 newtons, and Team B pulls south with a force of 560 newtons, then what is the resulting force in its direction? So again, this one's just a matter of subtracting, recognizing that you're subtracting. So you end up with 80 newtons moving towards the south. A lot of y'all probably did that one without even drawing your free body diagram. Number 12 says draw a free body diagram for a block sitting on a ramp. Label all the forces. So here's our block sitting on a ramp. We have our force of gravity, of course, pulling down. You should have your normal force at a perpendicular angle to the surface, and your force of friction parallel to the surface. Keep in mind, it's sitting still. It's not sliding down the ramp. There's no applied force. The key here, guys, is that all these forces must balance in order for it to stay sitting still. Number 13. Draw a free body diagram for a book sliding across a desk after being pushed. Label all of the forces on the book. So as it slides across, you still have the force of gravity and the normal force pulling on it. And then you have a force of friction causing it to slow down. Notice that it says it's after being pushed, so there's no reason to add an applied force because the applied force has already been added before we got started. Got a couple of bonus problems for you here. These will help you to practice some things that we talked about in class. First thing we have is a ramp at a 30-degree angle, and we have a block that has a mass of 15 newtons, or a force of 15 newtons pulling down on it, rather. You also have a force of friction that is 3 newtons. The question is, how much applied force is necessary to move the block? So in order to be able to do this, first let's go ahead and draw our free body diagram. So again, we have a 30-degree angle there. We have our force of gravity. We have a 15 Newton force that's pulling down. That is your force of gravity. The frictional force was 30 newtons, we said. Normal force we don't know. It's going to have to balance out. And then the applied force is what we're looking for. First thing I want you to recognize, the first thing I do here is I create another triangle, because what I have to recognize first is that if we're looking for the applied force, I have to make sure that I include all of the forces moving on the same plane as the applied force. We know that 3 newtons for frictional force is moving in the same plane. but we also have the force of gravity that we haven't found yet. We know the total force of gravity is 15 newtons, but part of that gravity is still on that same plane. The other part is on the plane that's equal with force of normal. So in order to separate those out, we're going to create this little triangle. Notice that if this is a 30-degree angle and we've got a right angle, then the other angle has to be 60. Then when we draw this other little triangle, we know that we have the hypotenuse of that triangle, which is 15. We know the angle is 60, so we can use cosine to try to find the adjacent side. The adjacent side should be the one that's right here that we're looking for. So cosine is going to cosine of 60 is going to equal the adjacent over 15 newtons. I'm going to multiply both sides times 15 newtons to get adjacent side by itself. So that's going to cause your 15 newtons to cancel out. Then when I plug this into the calculator, I get 17.5 newtons. So 17.5 plus 3 newtons gives us, sorry, not 17, 7.5 plus 3 newtons gives us 10.5 newtons. So that means that the force of acceleration is going to have to be greater than or equal to 10.5 newtons. Any questions on that one? Well, watch it again if you have any. Okay, looking at number 13, or I have one more bonus problem for you. In this bonus problem, I have two cars moving in opposite directions. One is moving at 30 miles per hour, the other one is moving in 50 miles per hour. What I want to know is, what is the speed of the green car relative to the red car? So in order to do this, we're simply adding the forces together. Keep in mind, on the other ones we've been talking about forces pulling on one object in different directions. This time we have two objects that are moving in different directions. If the two forces are acting on one object, then you subtract them because they're pulling it away from one another. This time we have two objects moving towards each other, so therefore you're going to add them together. So this one turns out at 80 miles per hour. Thanks for watching it. If you still have questions, watch it again. Work these problems on your own a few times. The best way to learn is to practice, practice, practice. Now that you know the answers, working the same problems will just help to solidify your understanding. Good luck.